Let's have a look at the iteration, if we can prove the iteration term, and we're going to use the method of the forward and backward substitution. Let's consider a simple sequence where an is an minus 1 plus 2. Basically what I'm saying here is that the next term is equal to the previous term plus 2. And the initial condition is a0 is equal to 3. So basically we start with the first iteration, a0 is equal to 3, and we can calculate a1, which is equal to a0 plus 2. a0 plus 2, a0 being 3 is 3 plus 2. So this is where we start with the forward substitution. a1 is a0 plus 2, it's equal to 3 plus 2, which gives us 5. Now we have a2, it's equal to the previous result, a1. Again, I add 2. And I find there this is equal to 5 plus 2. It's equal to 7, but I can also write it as 3 plus 2 times 2. And then we have a3, it's a2 plus 2. a2 being 7, I add 2 again, so I find 9, and basically I find 3 plus 3 times 2. And when I look at it, each time I'm multiplying the term 2 with the index of the term in the sequence. So with a3, I multiply 2 with 3. I can continue this until I find an, the last term, or the general term, as a function of an minus 1 plus 2, which is the basic definition that we had before. And we can say an minus 1 using the previous conclusion. I can say it's 3 plus 2 times n minus 1. So that's basically the term n minus 1. And in order to find an, I have to add 2 to this. And when I put the 2 in there, I have 3 plus 2 n minus 1 plus 2. I can put the 2 in the brackets because 2 times 1, I add it to n minus 1, and basically I find an is 3 plus 2 times n. Now we can start from the back. From the back we go from an. And I can say that an is an minus 1 plus 2. An minus 1 I can again replace by an minus 2 plus 2. And I add 2 to find an. So I find here an minus 2 plus 2 times 2. I continue, I replace an minus 2 by its expression, it's an minus 3 plus 2. I add 2 again and I find it's an minus 3 plus 3 times 2. And I can continue, so basically I go to an, which is then equal to a1 plus 2 times n minus 1. When I look at the elements, when I continue, I always find n minus 1. n minus 2 being n minus 1 is the n minus 2 term. So basically we continue and we know that a1 is equal to a0 plus 2 because that's the first term that we can identify. And when we put a1 in here, I find that an is a0 plus 2 times n minus 1. And when I simplify this formula, again I find an equal to 3 plus 2n. So basically we can find this term here that both terms are the same, and we have in fact proven the recurrence of the sequence. So that was it. We look at this example, but we have another example which is very interesting, which is the sequence of the compound interest. Compound interest is one of the main foundations in the topics of time value and finance, and the compound interest principle is at the basis of defining the future value, the present value, and the net present value. Those are very important parameters that we use in finance, that we use in investments, and that we also use in projects, for example, to evaluate how the investments are going and what the outcome of the project would be. Now, when we look at the term, the principle of the compound interest as a sequence, we will do that using an example. Let's say the initial conditions are, first of all, the deposit, which is $15,000, 15K. We have an interest rate of 5% per annum per year, and we have the period that we are considering N. So we want to know what happens with the compound interest at period N. Now, when we look at the recurrence is given by the value, the principal at period N, is equal to 1.05 times the principal at the previous period. We start with P0 equal to 15K, and from this we can basically deduct that Pn is 1.05 times Pn minus 1, but that it's also equal to 1.05 to N times P0. If we go through the series, we can go in both directions until both meet there, but it's in fact, when you want to know more about it, you can look at the videos that we have on YouTube and our courses about finance. You find that this is basically the formula of the compound interest. We keep the interest in the account and we keep applying the interest on the interest. And this creates an exponential growth factor. Of course, the higher the interest, the faster the growth. Now, when we look at 25 years, so we put those 15K in an account for 25 years, then we can calculate using this sequence that the principal after N periods, in our case 25 years, is 1.05 till the 25th power multiplied with the initial amount, P0. And that's approximately 48.7K. Now, I say approximately because I didn't look at all the decimals. We may have some more decimals there. Think about it when we are talking about projects, 48.7K could be sufficient. When we're talking to an accountant, they don't like the 48.7K. They look at the number up to the dollar cent. It all depends on who's looking at the numbers. When an accountant is looking at those numbers up to the dollar cent, don't think there is something wrong. It's their way to look at the numbers. And when you're looking at business, probably 48.7K would be more than sufficient. So basically, this was the part about the sequences, the iterations, and we looked at the forward and the backward method to verify the iterations. In the next session, we will be looking at special integers sequences. So that was it for this video. Thank you very much. I'm looking forward to seeing you in the next session. Thank you and bye-bye.